Welcome back to an introduction to real analysis. We continue going section by section. We're now in chapter 2, section 1, sequences and limits. What are we going to talk about here? Well, we have to begin with something I call a definition dump, a whole bunch of terms to define in order to talk about sequences and their limits. Now, most of the terms we introduce are fairly intuitive, people grasp them quickly, but the formal definitions inform how we actually prove things about sequences and their limits. Specifically, the formal definition of a limit of a sequence is in a very concrete sense the primary definition from which much of the rest of the course is going to follow. So it's incredibly important to learn that formal definition of a limit of a sequence. Intuitively understanding what limits are is great, don't get me wrong, but the formal definition is how you put together a proof. So learn it. It's not optional to learn the definitions of the things we're going to talk about. First, we start with definition 2.1.1. First, we're going to define what a sequence is. Now, a sequence is a function from the natural numbers to the reals, but in terms of notation, we typically do not write x of n, we write x subscript n, but it means the same thing. Okay, and we put the general term of a sequence inside this little curly braces. Down here is the starting index, up here is the finishing index, which typically is just infinity, there is no stop. A sequence is called bounded, either above or below, if the function is bounded. Remember, a sequence is a function. So if this list of values, the range of that function, is bounded above or below, then the sequence is called bounded above or below. Let's take a look at some examples. When we need to give a concrete sequence, typically the terms of the sequence will be spat out by a formula in terms of n. For example, if we look at 1 over n, then starting at 1, we get 1 over 1, then 1 over 2, then 1 over 3, and so forth. And this sequence is bounded. For example, it's bounded above by 1 and below by 0. On the other hand, if you look at the sequence just given by n goes 1, 2, 3, and so forth, that is not bounded. So the notation for a sequence is similar to that of a set, but they're not quite the same thing. Okay, so the sequence, negative 1 to the n equals 1 to infinity. Well, if n is 1, you get negative 1 to the first, negative 1 squared, negative 1 cubed, negative 1 to the fourth, and so forth. But if you were just looking at a set of values, that would be the range of the function. That just has two numbers in it, negative 1 and 1. The sequence really carries this notion of what comes next, what comes next. A set doesn't have an ordering in it. There isn't a first element of a set and a second one, and so forth. So another example of a sequence is so-called constant sequence, where this number does not depend on n. So for every n, you simply get the same constant over and over again. So this is a sequence where you simply repeat the same number over and over. As a sequence, it appears again and again and again. If you were just looking at a set of values, there would just be a single element. Next definition. This is the big one, okay? A sequence is said to converge to a number x if, for every epsilon which is positive, there is a natural number capital M, so that the distance between x sub n and x is less than epsilon for every n bigger than or equal to m. X is what we call the limit of the sequence. If this limit is unique, we will show that it is, we write the limit as n goes to infinity of x sub n equals x. A sequence that converges is something we call a convergent sequence. If it doesn't converge, we say it diverges or is a divergent sequence. Okay, again, this is a big definition. Spend some time to internalize it. The sequence converges to x if, for every epsilon which is positive, there is a natural number, so that for all indices past that m, the distance from the term of the sequence to the proposed limit is less than epsilon. So, more concretely, a sequence is said to converge to x, and here it is in terms of logical operators, which really tells us how we're going to prove things. For every epsilon which is positive, there exists an m in the natural numbers such that if n is bigger than or equal to m, then the distance from xn to x is less than epsilon. It's implicit here that n is a natural number. I did leave that out for clarity. So let's discuss what this definition means. In Prop 2.1.6, coming soon, we'll show that if there is a limit, there is only one. It is unique. So it makes sense then to talk about the limit of a sequence. It can only exist as a single unique thing. then we only need to show the sequence converges to one particular number. So for the next couple of examples, let's pretend we've already proved that there can only be one limit. We will eventually justify this in Prop 2.1.6. Now intuitively, the limit being x means that eventually every term of the sequence is very close to the limit in question. More precisely, we get as close as desired, arbitrarily close to the limit, at least provided we go far enough into the sequence. That's this existence of m, past which you have this absolute value being less than epsilon. It doesn't mean that the sequence ever achieves this value. It's possible, and indeed quite common, that no term of the sequence equals the limit. So let's take a look at a picture that might represent what's going on here. First, we're going to think of the sequence as a graph as we typically do, where our horizontal axis is our domain. So here is n equals 1, 2, 3, 4, and so forth, and this vertical axis is the real number line. And here is x1 is at this height, x2 at this, x3, x4, x5, x6, and so forth. Now here's a proposed x that might be the limit. It doesn't appear as if the sequence reaches this value. I mean, maybe this one's pretty close, but now we're really just guessing. However, the definition of the limit existing does not demand that the sequence ever equals it. It just has to be within epsilon. So we look at an epsilon allowable error. We want to get really, really close to x. We're happy if we are within plus or minus epsilon of x. So anything in this band is considered close enough. And in this picture, it looks like as long as you exclude index 1, 2, 3, and 4, if you start at index 5 and keep going, it certainly appears like every term of the sequence is as close as we want. And that's just for this particular choice of epsilon. You can imagine if epsilon was much, much smaller and this green tube was much narrower, you might have to go out further, not just exclude x1, 2, 3, and 4, but also x5, 6, and 7. And then maybe past that point, you're close enough. As long as for any particular choice of epsilon, eventually every term of the sequence is trapped in this tube, that's what the definition of the limit kind of represents. Now there's another way of drawing sequences, which is just to label the points on the number line. And I've done my best to make this picture match. So for example, x1 compared to x is a little bit above it. So there's x1. x2 is a decent distance less than x. x3, x4, x5, x6, x7, x8, 9, and so forth. Okay. Now, allowing an error of plus or minus epsilon to x is just represented by this little horizontal bar on the real number line. And with this relatively small value of epsilon, it looks like as long as we exclude index 1, 2, 3, 4, 6, so sure, exclude 5 as well, but past index 6, 7, 8, 9, 10, they all seem to be trapped here. Okay, as long as no matter how tightly you allow an error to exist, but this error epsilon does have to be positive, no matter how small you make it, eventually all terms of the sequence are as close as desired. But again, I do want to stress the formal definition does tell us how we're going to construct proofs, so don't skimp on that one. Okay, so this definition is a big deal. When we write the limit as n goes to infinity of xn equals x, we're saying two things. First, the sequence converges, and second, that the thing it's converging to is specifically x. The fact that this limit equals something tells us the sequence is converging, and then this particular number is what the limit is. Okay, this is one of the most important definitions to really master, so please, for your own good, do your best to understand it. The key point in the definition is that it has to apply for any positive epsilon. No matter what epsilon you pick, as long as it's positive, this inequality has to be achievable. Not necessarily for every term of the sequence, but for terms past a certain point. What point? Well, it just has to exist. Now this m can certainly depend on epsilon. Okay, so you only have to pick the cutoff index m after the epsilon is declared. For every epsilon, there is an m. If you change epsilon, m might change. So here's an example, 2.1.3. A constant sequence. Does it converge? Yes, it converges to whatever that number is. So let's actually put together a proof. You may be rolling your eyes and saying, obviously it's converging, but it's important to master the definition of a converging sequence having a specific limit so that you can put together a proof. First, for any epsilon which is positive, let epsilon be a positive number. Now we have to concoct what the cutoff point m is. I'm just going to pick m equals 1. Now I have a conditional statement, assume the hypothesis. Assume n is bigger than or equal to the m you just picked. Well, what do I know about x sub n for this choice of n? Every term is c. So now let's look, did we achieve our inequality? Xn minus x, well, we claimed the limit was c, and also xn is c. What is c minus c? It's 0. Is 0 less than epsilon? Yes, that is how we picked epsilon. It had to be positive. So we have formally proved that a constant sequence does converge to whatever that constant is. Here's another example. The sequence 1 over n, 1, 1/2, 1/3, and so forth, converges to 0. So let's look at a proof. Again, it's important to know this definition so that you know how to put together a proof. It must apply for every positive epsilon. Let epsilon be positive. Now we have to pick the m. Now in contrast to the previous example, we have to be a little careful here. So the Archimedean principle, which I've reminded us at the right, says there is an m so that m times epsilon is bigger than 1. That's that first form of the Archimedean principle. Since epsilon is positive, and I can pick y equals 1, there is a choice for which m times epsilon is bigger than 1. Divide both sides by m and you get 1 over m is less than epsilon. So the Archimedean principle tells us there is a capital M so that 1 over m is less than epsilon. It does depend on epsilon, what this m is, but as long as epsilon is positive, it must exist. So I'm going to pick that to be my m. Now I have a conditional statement, assume n is bigger than or equal to m. Great. So x sub n is 1 over n. That's how the terms of our sequence were being generated. Since n is bigger than or equal to m, 1 over n is less than or equal to 1 over m. So now let's look at this inequality here. X sub n is 1 over n. Our claimed limit is 0. 1 over n minus 0 is 1 over n. And what do I know about the absolute value of 1 over n? It's less than or equal to 1 over m, and 1 over m is less than epsilon. So we got less than epsilon as needed. So we have proved that the sequence 1 over n converges to 0. All right, let's take a look at another example. We still have the definition of a sequence converging up in the upper right for reference. Let's look at the sequence minus 1 to the n. So it goes minus 1, positive 1, minus 1, positive 1. We claim this doesn't converge at all. It's divergent. So assume to the contrary that the above definition does hold for some choice of real number x. So we're assuming to the contrary that this is a true statement for some number x. Well, this has to apply for every positive epsilon. So pick epsilon equal to 1. There must exist a capital M, so that as long as n is bigger than or equal to capital M, the distance from xn to our proposed limit x must be less than epsilon, and we picked epsilon equal to 1. So negative 1 to the n minus x must always be less than 1, at least once n is bigger than or equal to this cutoff index, capital M. But whatever m is, both 2m and 2m plus 1 are bigger than it. So I have an even number and an odd number bigger than m. My sequence will therefore spit out a positive 1 and a negative 1. So this inequality that I'm highlighting in the upper right must apply for a 1 and a minus 1, whatever x is with epsilon equal to 1. This gives two contradictory statements. First, the distance from 1 to x must be less than 1. This tells me that x must be bigger than 0. But the distance from minus 1 to x must also be less than 1, so x must now be less than 0. X cannot be both bigger and less than 0. So there is no limit to this sequence. Okay, at long last, proposition 2.1.6, a convergent sequence has a unique limit. More specifically, if the limit of the sequence xn is x, but it is also y, then x must equal y. Don't just think you're just going to use transitivity of the equal sign, by the way. We aren't really justified in using the notation of this equal sign until we establish this result that the limit is unique. Okay, so how are we going to prove this? Assume that the limit of xn is x and the limit of xn is y. Now let epsilon be an arbitrary positive number, so half of it is positive as well. Now let's remember this definition. We are assuming that this definition holds for x, but also for y. Epsilon over 2 is positive, so there exists an m1, so that past that point we have that xn is very close to x. However, since I assumed this also held for y, there is a presumably different m2, so that past that point, the distance to y is less than epsilon over 2 as well. Now if I pick capital M to be the larger of these two numbers, once I am past capital M, I am past both m1 and m2, meaning both of these inequalities will hold. So past this new cutoff m, let's just look at the distance between x and y. First we do the standard silly trick of adding 0, so we have a plus and minus xn inside the absolute value. By the triangle inequality, I now have this number plus this number in an absolute value, so I can say it's less than or equal to the absolute value of the first plus the absolute value of the second. But as we just said on the previous slide, since n is bigger than or equal to this cutoff m, this is less than epsilon over 2, but so is that. Epsilon over 2 plus epsilon over 2 is just epsilon. So the absolute value of x minus y is less than epsilon for every positive epsilon. Back in chapter 1, we showed that the only number whose absolute value is less than every positive epsilon is 0. So the absolute value of x minus y is 0, therefore x minus y is 0, therefore x equals y. And the proof is complete. Okay, so we're not claiming every sequence has a limit, just to be clear. But if the limit exists, there can be only one, which justifies using the equal sign. The limit equals something. There is only one number that will work there. Okay, again reminding us of this important definition in the upper right, let's look at proposition 2.1.7. A convergent sequence must be bounded. So we are assuming that this statement holds. The sequence is converging to x. Since this must be true for every positive epsilon, let's just pick one, specifically 1. Then there must be a capital M, so that for every n past capital M, the distance between xn and the limit x must be less than epsilon, and we picked epsilon equals 1. So now let's do a quick computation. The absolute value of xn, as long as we are past that cutoff point, well, we can always do this minus x plus x. Now I have one term plus another, so triangle inequality, but the distance between xn and x is less than epsilon, aka 1, as long as we are past the index capital M. So for every n bigger than or equal to capital M, the absolute value of xn is less than 1 plus the absolute value of x. And observe that x is a constant. It is whatever the limit is, and there's only one such number. So now let's let capital B be the maximum of this finite set. First, the absolute value of x1, absolute value x2, all the way up to absolute value of x sub m minus 1, whatever this m is. Include all these absolute values, and then stop, and then throw in the single value 1 plus the absolute value of x. Pick the biggest number out of this finite list. Remember, every finite set has a maximum. This is an exercise back in chapter 1. Now, as long as I is less than capital M, x sub I appears in here. And since we picked a maximum, the absolute value of xi cannot be bigger than whatever we picked. So the absolute value of xi is less than or equal to b as long as I is less than m. But if I is bigger than or equal to m, then the absolute value of xi is less than 1 plus the absolute value of x, which was one of the things in the list, and we picked a maximum. So the maximum is bigger than or equal to one particular element of this list. So whether I is before m or after m, the absolute value of xi is always less than or equal to b. Okay? And if the sequence of absolute values is bounded, that means the sequence is bounded. The converse of the previous proposition does not hold. Okay, a sequence which is convergent must be bounded, but it doesn't mean every bounded sequence must converge. One of our previous examples was that the alternating sequence 1 minus 1, 1 minus 1 doesn't converge, but it's definitely bounded, above by 1 and below by minus 1. Okay, so while every convergent sequence has to be bounded, do not make the mistake of thinking any bounded sequence must converge. Now let's look at example 2.1.8. Look at the sequence n squared plus 1 over n squared plus n. We're going to show that the limit is 1. So let epsilon be positive, Again, knowing this definition is crucial in proving things. We want to prove something holds for every positive epsilon, so let epsilon be positive. Again, we're going to use the Archimedean principle to find a capital M so that 1 over m is less than epsilon. Now, if n is bigger than or equal to that, we work through the following steps. The term of our sequence minus our proposed limit. So n squared plus 1 over n squared plus n minus 1. Well, let's give them a common denominator. Simplify that numerator. Now, in absolute value, 1 minus n, as long as n is larger than 1, this numerator is definitely negative, this denominator is definitely positive, so I can compute the absolute value like this. Now observe that this n minus 1 is definitely less than n. I can then cancel these n's and get 1 over n plus 1. Since n plus 1 is bigger than n, 1 over n plus 1 is less than 1 over n. N was at least as large as m, so this is less than or equal to 1 over capital M, but 1 over capital M was less than epsilon. Altogether, as long as our index is bigger than or equal to this cutoff, again, that was given by the Archimedean principle, the terms of our sequence minus the proposed limit in absolute value has to be less than epsilon. Okay. Not every proof, by the way, begins with saying by the Archimedean principle. It's just we don't have a whole lot of tools to work with at this point, so the ones we've done so far do. Moving on, an important little subsection, monotone sequences. Other than, I suppose, than constant sequences, often the easiest type of sequence to consider is a monotone one. We'll introduce the definition shortly, but checking whether or not a monotone sequence converges is, in fact, just as easy as seeing if it's bounded. This provides a partial converse to proposition 2.1.7. Not every bounded sequence has to converge, but a bounded monotone sequence does. These are things we will prove shortly. Okay, it's also fairly straightforward to find the limit of a converging monotone sequence. It's just defined in terms of some sups or infs of a countable set of numbers. So let's give the definition now. A sequence is called monotone increasing if one term of the sequence is less than or equal to the next. It's called monotone decreasing if you get the reverse inequality. So if a sequence is either monotone increasing or monotone decreasing, you just call it monotone. So if we say, consider a monotone sequence, that will immediately say there's two cases. It's either monotone increasing or it's monotone decreasing. It's worth pointing out, not every sequence is monotone. Of course, for two numbers, one of these two inequalities will hold, but we need the same inequality to hold for all indices. That is not always going to happen. So let's take a look at some quick examples. The sequence of just n, 1, 2, 3, 4, that's monotone increasing. Every term is bigger than or equal to the one before it. 1, 1/2, 1/3, 1/4, that's monotone decreasing. Every term is less than or equal to the one before it. A constant sequence is actually both. If you simply repeat the same number over and over again, you are both bigger than or equal to and less than or equal to the one before it. But the sequence minus 1 to the n is neither monotone increasing nor monotone decreasing. 1 minus 1, 1 minus 1. You go down from 1 to minus 1, but then you go up from minus 1 to plus 1. Since the same inequality cannot be held from every term to the next one, you are not monotone increasing, but you are also not monotone decreasing. Do not think that calling a sequence not monotone increasing automatically means it's monotone decreasing. Most sequences will be neither. Okay, here is a very important theorem, 2.1.10, the monotone convergence theorem. A monotone sequence converges if and only if it's bounded, in which case a monotone increasing sequence must be converging to its supremum, and a monotone decreasing sequence must be converging to its infimum. All right, so let's take a look. We're just going to do the monotone increasing case. The monotone decreasing case is essentially the same thing. So we need to prove that a monotone increasing sequence converges if and only if it's bounded, in which case it converges to its sup. Well, first of all, if it's converging, it has to be bounded. That's prop 2.1.7. So if it converges, it must be bounded. So all we need to do is show that if it is bounded, it is converging to its supremum. So let's suppose we have a monotone increasing sequence. It's bounded. Let's call x the supremum. We want to show the sequence converges to x. Okay, and the definition of a sequence converging had that for any positive epsilon, so let epsilon be positive. X minus epsilon is less than the sup of xn. Why? Because this is x, so x minus epsilon is less than x. Since we are now less than the supremum, we are not an upper bound of the sequence, meaning there is a term of the sequence bigger than x minus epsilon. Since x minus epsilon is less than the supremum, it's not an upper bound. Since it's not an upper bound, some term of the sequence is bigger. But the sequence is monotone increasing, so every index past this capital M is bigger than or equal to the one we just had, meaning every term past capital M is also bigger than x minus epsilon. But x, remember, was the sup of the sequence. It is an upper bound, so every term of the sequence is less than or equal to x. So putting these two things together, as long as we are past this cutoff point of M, every remaining term of the sequence is between x and x minus epsilon, meaning its distance to x is less than epsilon. So if the sequence is monotone increasing and bounded, it must be converging to its supremum. Let's look at boundedness in monotone sequences in a little more detail. A monotone increasing sequence is always bounded from below. Since every term is bigger than or equal to the one before it, the first term acts as a lower bound on the sequence. So to see if a monotone increasing sequence is bounded, you just need to check if it's bounded above. Similarly, a monotone decreasing sequence is always bounded above, so it's just enough to check if it's bounded below. So let's take a look at an example. Look at the sequence n to the minus 1/2, in other words, 1 over the square root of n. We claim this converges to 0. Now, n is just getting bigger, so the square root is just getting bigger, so 1 over the square root is just getting smaller. So this is a monotone decreasing sequence. It's definitely bounded below. Every 1 over root n is positive, so it is bounded below by 0. So now we have a sequence that is monotone decreasing and bounded below. Therefore, it has a limit. And in fact, all we have to do is find the infimum. We know 0 is a lower bound. We claim that it's actually the infimum, so it's the biggest lower bound. So we want to claim that the infimum of this sequence is 0. So suppose you have a number bigger than or equal to 0, which is a lower bound. So this number must be less than or equal to every 1 over root n. Squaring both sides, b squared must be less than or equal to 1 over n. Therefore, b squared must be less than or equal to 0. We've already established that this sequence, 1 over n, has limit 0. So it gets arbitrarily close to 0. So if b squared is less than all of them, it must also be less than or equal to 0. But the square of any real number can't be less than 0, so it must be equal to 0. And if b squared equals 0, then b equals 0. So the only non-negative number, which can be a lower bound, is 0 itself. Therefore, it must be the largest lower bound. Okay, now that we have found the infimum of this sequence, since it was monotone decreasing and bounded below, we found its infimum. That means we found its limit. A word of caution is in order. Showing that a monotone sequence is bounded in order to use this result can be kind of difficult. Consider the following sequence of Sn, where it's the sum of the fractions 1 over 1 plus 1 over 2 all the way up to 1 over n. This is monotone increasing. To get the next term, I would add 1 over n plus 1. I would make it bigger. Then add 1 over n plus 2. Make it bigger. It's definitely a monotone increasing sequence. However, it grows very slowly. It grows slower and slower as n gets larger. But once we have a little bit more terminology and tools under our belt, this sequence does not have an upper bound. It doesn't converge. But just numerically, just throwing this into a computer and asking it to compute a whole bunch of terms, it's not obvious that this does not have an upper bound. Now we have proposition 2.1.13, a nice little result we'll cite once or twice in the future. The proof is left as an exercise. We're merely stating the result here. Suppose you have S, which is not empty and is bounded. Then there are monotone sequences xn and yn that satisfy a few conditions. First, they're drawn from the set S. So every element of both sequence drawn from the set S. However, xn is converging to the sup of S and yn is converging to the inf of S. Basically, if you have any non-empty bounded set, you can make a sequence of elements of that set converging to the sup, and you can make a sequence of elements of the set converging to the inf. Again, we're not proving that here, just stating it. Let's move on to tails of a sequence. We're going to discuss what that is. Now, calculus follows from understanding limits. Limits establish with dealing this inequality, but it only has to hold past a certain index. We do not demand that every xn minus x be less than epsilon, only those where n is past some cutoff point, capital M. In other words, the first few terms of a sequence are irrelevant when talking about limits. You don't really care what the sequence is doing when the index is small, but small has to be in kind of big air quotes here because we don't know what small versus big really means. And defining what a tail of a sequence is really clarifies what's going on here. So here's the definition. Given a sequence, the k-tail of the sequence is given by any of the following equivalent formulations. The first is all the terms of the sequence beginning at index k plus 1. This is all terms of the sequence, but taking away all of them up to index k. And here, you simply add k to every index. Therefore, your smallest index is k plus 1. All of these are the same thing. It just means every term of the sequence, but only past the kth index. So what are some examples? The zero tail of a sequence is the original sequence. You have cut out 0 terms. The 4 tail of 1 over n, the 4 tail tells me I'm removing 4 terms. So I'm going to start at 1 over 5, and then I keep going. Okay, now what we'll do is we'll show that convergence of a sequence is purely a property of whether the tails converge. The first several terms are irrelevant. It's only what's happening in the tail that matters when talking about limits. Here it is, prop 2.1.15. Suppose you have a sequence. The following statements are all equivalent. The sequence converges to x, every k-tail converges to x, some k-tail converges to x. So we want to prove these statements are equivalent, so any one of them can imply the others. So we have 3 things here, 1, 2, and 3. This arrow here, well, first of all, if every tail converges to x, then definitely at least one of them does. So 2 implies 3, very straightforward. 1 implies 2 is also pretty straightforward. If the sequence converges to x, then consider any particular k. Define yn to be this version of the k-tail. Add k to every index. We just need to show that the k-tail, the yns, converge to x. So let epsilon be positive. The original sequence converges by assumption. So past a certain point, xn minus x is less than epsilon. But what's yn? It's just x's with larger indices. So those are also close to x. Because the sequence was presumed to converge to x, every term past a certain point satisfies this inequality. Yn simply makes the indices bigger, so they will also obey the same inequality. So if the sequence overall converges to x, so does every k-tail. Okay, finally, let's see that the third item proves the first. Suppose there is a k, so that the k-tail converges to x, and we're going to use this formulation again. Now let epsilon be positive. There must be a capital M, so that the y's are within epsilon of x. Now let m prime just be m plus k. Then if n prime is bigger than m prime, then n prime has to be n plus k for some n bigger than or equal to m. If I'm bigger than this, then I am a plus k compared to something bigger than m. So then you can set xn prime equal to yn. The distance from xn prime to x must be less than epsilon, so the original sequence converges to the same limit as well. The tail notion here just sort of shifts what indices you're talking about, but since the definition merely asks there to be some cutoff point, it doesn't matter if you slide it over by a few indices or not. Okay, so overall, if every tail converges to x, certainly one of them does. If the sequence converges, then so does every tail. And if one of the tails converges, so does the sequence. So they all imply one another. Let's talk about this word eventually. Okay, so a very common modification of definitions, also later functions, is this term eventually. So for example, eventually monotone. We can call a sequence eventually monotone if there is a tail of the sequence which is monotone. In other words, if I cut out finitely many terms and only look at what happens eventually, then what's left is monotone. So consider the sequence n over n squared plus 16. if we start computing the terms, we get 1 over 17, 1 over 10, 3 over 25, 1 over 8, 5 over 41. Okay, this is eventually monotone. In fact, if you cut out the first, second, and third term and just start looking here, this is now going to be monotone decreasing. But the first few terms violate that. I get bigger here, and I definitely get bigger here. Okay, so the first few terms jump around a little bit, but if I only look at the three tail, what remains is monotone decreasing. So we would call this eventually decreasing. Okay, so the tail is monotone decreasing and bounded below by 0, so the tail converges. Okay, ignoring the first three terms, we are eventually decreasing. I have a tail that's decreasing. Every term here is definitely bigger than or equal to 0, so it's bounded below. The tail converges, and as just established, if some tail converges, the original sequence does as well. All right, an important topic, subsequences. Subsequences are somewhat similar in motivation to tails, but a lot less restrictive. A tail of a sequence ignores the first k terms, but then after that you have to keep everything. A subsequence has a lot more freedom as to what terms of the sequence you do want to preserve and which you ignore. There are some restrictions. You have to keep infinitely many terms of the original sequence, and you have to respect the order of indices that they came with. So let's formalize that definition now. So here is the definition of a subsequence. Suppose you have a sequence. A subsequence is given by x sub n sub I, where n sub I is an increasing sequence of natural numbers. Strictly increasing simply means not allowing for equality in the monotone increasing definition. So n1 has to be less than n2, has to be less than n3. You have natural numbers here that are definitely getting bigger, and those form the index of your subsequence. So a subsequence is something like x sub n1, x sub n2, x sub n3, and so forth. Consider 1 over n, so 1, 1/2, 1/3, 1/4, etc. 1 over 3i is a subsequence. Okay. Take, for example, n sub I equals 3i, so 3 times 1, 3 times 2, 3 times 3. These are natural numbers, and they are getting bigger. So 1 over n sub I forms a subsequence. So you would have 1 over 3, 1 over 6, 1 over 9, 1 over 12. Those are terms from this sequence in the order they would have appeared in that sequence. Okay, you do have to come from the original sequence. So if I did something like 1, 0, a third 0, a fifth 0, a seventh 0, that's not a subsequence of 1 over n. These zeros are not in the sequence that I started with, not a subsequence. Also, you have to preserve the order the terms appeared in. 1, 1/3, a half, a fifth, those are all terms of this sequence, but they're in the wrong order. A half would have to come before a third. Okay, it's fine that a quarter is not in there. It's a subsequence. You can omit certain terms, but those terms you do keep have to be in the same order that they were in the original sequence. Okay, a tail of a sequence is a special type of subsequence, just given by n sub I as I plus a constant. For an arbitrary subsequence, we do have a proposition about convergence. It's going to be very useful for us. Let's look now at proposition 2.1.17. Given a sequence xn, the limit is x if and only if every subsequence also converges to the same x. Let's take a look at the proof. So if I just consider n sub I equals I, 1, 2, 3, 4, and so forth, that is an increasing sequence. That is to say, a sequence is a subsequence of itself. So if every subsequence is converging to x, the original certainly does as well. Another argument which is equivalent here is that tails are a very particular type of subsequence. So if every subsequence converges to x, the tails have to converge to x, and as previously argued, if any tail converges to x, then so does the original sequence. So one direction of this proposition is quite straightforward. If every subsequence converges to x, then the original does as well. The other direction takes a little bit of care. Suppose the original sequence converges to x, and now let's consider an arbitrary subsequence. So we have x sub n sub I, where n sub I is an increasing sequence of natural numbers. It's a pretty quick inductive proof to show that if ni are increasing natural numbers, ni must be at least as big as I. n1 has to be at least as big as 1. n2 is bigger than n1, which means it's at least as big as 2. n3 is bigger than n2, which means it's at least as big as 3, and so forth, okay? So now, let's let epsilon be positive. The original sequence was assumed to converge to x, so there is a cutoff point past which every term of the sequence is within epsilon distance of that limit x. But what does that tell me about the subsequence? Well, if I look at an index past the same cutoff, okay, n sub I is at least as big as I is at least as big as m, so n sub I is at least as big as m. Now this inequality here for the original sequence held for every term whose index is bigger than m. While here is an index that's bigger than m. Therefore I get this inequality. Overall, as long as I is bigger than or equal to m, x sub ni is within epsilon of x. In other words, the subsequence is converging to x. Finally, let's look at example 2.1.18. Okay, if a sequence converges, we've just shown that every subsequence converges to the same thing. But a sequence can have certain subsequence converging without the original sequence converging to anything. So consider a sequence. Here's a nice expression for it, but really you just have to know it goes 0, 1, 0, 1, 0, 1, 0, 1. Every other term is a 0. So if I look at index 1, index 3, index 5, index 7, and so forth, that gives me 0, 0, 0, 0. That's a constant sequence that converges to 0. But if I look at the indices given by 2, 4, 6, I get 1, 1, 1, 1. So the even index subsequence is constantly 1 converging to 1. So if I have two subsequences that converge to different limits, the previous proposition actually says the original can't converge to anything. Remember, the previous proposition was a sequence converges to x if and only if every subsequence converges to the same x. So if there are two subsequences converging to different things, the original sequence cannot converge to anything. Let's review what we've discussed. Okay, limits are absolutely crucial in analysis. Learn the definition of the limit of a sequence. Epsilon and everything. It's great if you think of it in terms of a picture or something like that. Do not let that lull you into a sense of security that you don't need to know the epsilon definition. Okay? Know the actual definition of a limit of a sequence. Don't just rely on intuition here. The formal definition tells us how to put together a proof involving limits. Okay, moving on to actual important results. This is a big one. If a sequence is bounded and monotone, then it must converge. Okay, and a sequence converges if and only if all the tails converge to the same thing, if and only if all subsequences converge to the same thing.